Okay, so today is Sunday, August 10th. We have migrated our Sunday meeting a week early. We have with us a special guest, Asa Gordon, who was an astrodynamicist at NASA. He worked at NASA for 25 years. And the reason that Asa's with us today is because he took his math work, very complicated math work, and implemented it on the Timex Sinclair 2068. And I'll let Asa get into the details, but as he was just telling me a few minutes ago, the results that he got on his tiny little computer, the one behind me, were as good as the results that other folks were getting on their IBM mainframe. So Asa, um, first of all, what is an astrodynamicist?
An astrodynamicist is the one who deals with the mathematics that governs the motion of artificial bodies in space. So that's it. It's just orbital. It's uh, calculation the orbital mechanics that let you know where you are in space. that's
Okay,
that's
okay.
basically it.
Kind of important to know when you're in space, right?
Right.
All right. And before we get to the 2068 part,
Mhm.
uh, I want to know about you. So, you know, take me back to the beginning of your journey.
Okay. My all of my education was under Jim Crow law.
Mhm.
So my elementary school, my secondary education, my high school was under Jim Crow. I attended an historical black college called Hampton Institute in Virginia. I attended that on what was called an out-of-state aid. That, in essence, was the state of Georgia would pay me since they would not allow me in the University of Georgia. They would pay me to go tuition if I attended in my field outside the state. And that's how I attended Hampton Institute. I majored in physics and minor in mathematics. There were no courses in space science at that time. Now I'm gonna have to skip forward and a number of years from my graduation from Hampton Institute, which was around oh, 1862.
No, no, no. It
Not
was later than
19,
that.
1962. I'm sorry, 19. Look, I'm 85 years old, so catch me on it. So 1962, and so I ended up at Howard University around the late 60s. This is after I had spent years in dealing with the civil rights movement and demonstrations and voter registration drives and all that kind of stuff. Okay.
Cool.
All right. Now I'm at Hampton. I'm in the computer lab. I find my way to make a little change. I was talking to working in the computer lab at Howard University. And that was my first, and I was programming in FORTRAN, which
Cool.
was a high level language for what we call formula translation, and to do computation for graduate students, who are on the computer. I think the input was a 80 punch card, 80 column
Pretty
punch
common punch
card,
cards, yeah.
and real tape, you know.
Hmm.
And IBM 1620, I think it was 64 kilobyte megabytes. I'm not sure. Uh, and anyway, so while I was there, the word got out that Goddard Space Flight Center, which was in Greenbelt, Maryland, kind of suburb of Washington D.C., was looking for programmers.
Hmm.
And I always was interested in getting into science. I said, by the time I get any kind of advanced degree, these guys will be on the moon and back. Heck with this. I'm taking the first chance I get to get into the space program. So I applied to be as a programmer, you know, mainly as a mathematician programmer for
Okay.
Goddard Space Flight Center. And I was accepted. And fortunately, I was accepted. When I was accepted, it was a time when they were two, I don't know if you saw a movie called Hidden Figures.
Yeah.
Well, my both my branch head and my section head were hidden figure types. Well, my branch head was African American woman, and my section head was African American.
Oh,
So and it was the orbital, and I fell into, by luck, it was called the orbital analysis prediction branch. And what we were doing, we were programming theories to deal with satellites in orbit,
mhm.
and we were programming that programming on punch cards, and then we would load the punch cards of those calculations of the formulas that was handed down to us. Now, at this time, I was fascinated by what I was programming, and I wanted to learn about this, what I was doing, what I was programming.
Mhm.
And so once a month, I talked to my supervisor, and I said, look, I want to teach myself about this field. She was very interested in that. She said, okay. I say, so once a week at the beginning of the month, I want to be able to go to the Goddard Library and check out journals on this. And she said, you got it, you know. And so the first of the month for my first year at Goddard, I would go to the library and check out everything I could read on in the field of celestial mechanics. And so my and actually, I think that this turned out to be a plus that I did not have formal training in this, because it, it I found out later that I was thinking outside the box, and I was thinking outside the box because I hadn't been programming what the box was supposed to be,
Right.
by teaching myself, the field. Um, and so it came up. My first mission that came up. Now I want you to understand that I was doing at uh, Goddard during the Apollo years, in the most all of the Apollo years, and the shuttle years.
Okay.
That's so all most of the manned flight years I was involved. It was my fortunate to be associated with NASA. The first mission I was programming. She asked me, my supervisor Melba Mouton, a hidden figure. She said, "Look, I want you to look into the problems we're having with communications on this first mission to circumnavigate, first crewed mission of man to circumnavigate the moon. It was
Uh-huh.
called the figure eight trajectory. And what came out of that, most people familiar with the Earth rise, and um, the
Yeah.
pictures that came out of that, first picture of the Earth rising over the horizon of the moon was
Oh
taken on that
gosh.
mission. Well, what she wanted me to do was to compute to look at the program for the radio blackout that would occur when the mission was on the on the dark side of the moon.
Mhm.
And when I looked at it, I said, I was kind of surprised. I said, they used what is called a cylindrical model. Cylindrical model meant that it was just a cylindrical shadow that was cast. And I said, that doesn't seem right. What about the partial, graduation of the sunlight of the when they enter what we call a penumbra and umbra region. The
Mhm.
penumbra region, when you see a partial part of the disk, and umbra would be when you have a total eclipse and you would have total darkness. And so I decided to that's what was in the Goddard trajectory determination system. That was the main programming system for our missions. So I decided to look into if I could add penumbra region and the umbra region when it entered into partial light, and then it would go. You see a little bit of the disk, and you still get a little bit of radio signal, but the radio signals would be scattered. It'd be less communal.
Okay.
And I use Keplerian dynamics. That was from basic physics. Just as a side, I found out that one other advantage I had is most of the uh, people I was involved with was in mathematics. I had an advantage in being in physics. In physics, you were taught to do what they call vacuum analysis, where you you picture things where there's no friction and a vacuum,
Uh,
and then you kind of build upon that to build your algorithms. In physics, you have more of a incentive to visualize a problem rather than just start calculating because you can calculate,
right.
we tend to dream more, imagine, like, so I imagine myself being a little particle out there, the satellite in space, and I'm going along. I say, well, I look back at Earth, I'm going to see a little bit of the house, and then all of a sudden, and so I remember I went to an art store and I got some styrofoam balls, and I got a flash, and I shined a flashlight on a styrofoam ball, and I had a little ball to go around the other ball to see what it would look like, the shadow would look like as it go on that. I was in the apartment then, and I was doing that in the second, and that gave me an idea. And for the first time, all of that time when I was in high school, I was taking geometry, and I said, "What in the hell is that? Am I going to ever use this?" My God, it was beautiful. It was pure geometry. Now, if we have time, I'm going to show you the slides that I put together in order to click what is called a solar flux. That is the percentage of total sunlight that's available, depending on two disks when they intersect, and the eclipse is taking place.
Wow.
That's available to a spacecraft or an observation.
Mhm.
All right, so I'll show that later in the slide. All right, so I was able to use that to predict. So, I wrote a routine. Now, that was the first time now I'm doing more than programming. I'm doing the mathematics. And I wrote the mathematics. I did the mathematics in that program, my own mathematics, to predict the time and entry and exit from penumbra and umbra uh, of the Apollo 8 mission. And I remember when I was when I was called out, it was on Christmas Eve. Uh, Melbourne called me out to run my program, and I was kind of nervous. It's physics. I shouldn't be nervous, science. So, but it was counting down and say exactly when the cutoff would be of radio signals, and when the cutoff, what they call AOS, and that was the acquisition of signal and loss of signal.
Mm.
And when my program said, 10-9-0-1, it was dead on, and I got this kind of ovation in the realm, and oh yeah, interested aside, when I reported to the what was it, off to the control room, they wouldn't let me in, and I said, well, I have the badge here, and they said, well, you can't. And I found out later what it is all this stuff I did when I was in civil rights. Evidently, I have an FBI file for, being a demonstrator or something like that. And so I didn't have clearance. And so Melba came down and said, well, this guy, we're running his theory, so he knows what he did. So I was let in, to observe the running of that particular thing. Sorry to go off there.
Oh no.
So now I'm going to start we share my screen.
You're gonna have to reshare it. Yeah.
Okay. And I want to go to the slides, hopefully of the I click on.
Did you have the slides in? Oh, PowerPoint. Okay.
Okay. This is the old PowerPoint, man. All right, this ain't the new one. All right. All right. All right. Okay, and let's see. I'm gonna start the slideshow.
Yeah.
Can everybody see that?
Yeah. Perfect.
All right. So first slide. As an astrodynamicist, GSFC, Goddard Space Flight Center, NASA in the 1980s, I programmed my satellite orbit theory and Sinclair basic on the Sinclair. Let me move down here. I can't see myself. Okay. All right. Timex Sinclair 2068 and revolutionized the field of orbital mechanics that set the foundation for autonomous onboard satellite orbital navigation. Autonomous meant that it could, do it.
Itself.
The satellite could do its own calculation without depending on ground contact with ground station.
Right.
These are the two critical papers. The first time I presented this at Reno, Nevada, I presented at the Aerodynamics International. I forget what they are.
American Institute of
Some for International Aeronautics, something like that. Yeah. Okay. An economic semi-analytical orbit theory for microcomputer applications. Now, this is the NASA paper where that was the paper I presented at the conference, and that became the NASA technical paper. It's in that technical paper that I have the actual coding in BASIC, and that's an actual image of the
your ID card.
Oh, this is the.
You have you still have your 2016. Very nice.
This is the actual artifact that changed dynamics. Okay. And so that's going to be part of the artifacts that I'm going to add to the archives. That's one of my badges on the space shuttle. That 3 doesn't mean I was 3 in line. I don't believe. I want you to understand that doesn't mean I was number 3. Okay, there were tens of thousands of 3s. Okay, and so let's see. Well, Gordon's breakthrough on the time at Sinclair. I think this was in the email, but it said in the mid 1980s, Robert Gordon proved professional grade orbit propagation could run on the 8-bit on computer. He ported his PG semi-analytical perturbation theory onto a Timex Sinclair 2068 using his Z8 CPU and 48 kilobyte RAM to generate multi-day ephemeris. Ephemeris mean, orbits, what the coordinates were, X, Y, Z.
Okay.
And the actual elements that describe what a satellite, when you say an ephemeris, that is a list of position points in space.
Okay.
Okay, with sub 2 kilometer accuracy. By blending BASIC for high-level logic and hand-tuned Z8 assembly. Now, I want you to understand, I don't know what I'm talking about there. for the heavy lifting math, he showed that users no longer needed mini computers or mainframes to predict satellite motion. Technical innovations. Now, these technical innovations had to do with 2068, nothing I did.
Mm-hmm.
Memory banking, Gordon leveraged 2068 bank switching. Of course, I didn't know I was doing that. Hardware to juggle code, data tables, and intermediate orbit elements in 8 kilobytes pages that I understood, squeezing his entire propagator into limited memory.
Wow. Now,
this is pseudo-physical drag model. Most astrodynamics still can't figure out what the hell I was doing there. That's why it's called pseudo-physical. I'll try to explain it later. He implemented his secular drag relationship directly into semi-major axis update routine, avoiding complex lookup tables and keeping runtime lean. Now, secular, when you have motion, secular means a slow decay. It would be like linear,
Okay.
As opposed to wave motion would be oscillating, like sine and cosine. Secular would be like the mean motion that the oscillating wave would be oscillating around,
Okay.
So mean motion, think of a slow decay. And
right.
What I was, and in essence, what that is saying, well, if you're going through, and this is where I imagine, say, if I'm a little particle and I'm up there in the atmosphere and I'm trying to fight my way through the atmosphere, I'm meeting resistance. So I'm going to lose energy. And as I lose energy, it would be gradual, and I would, I would fall down into, to to
It's the
Earth,
atmosphere.
you
Yeah.
know. And so I imagined that the satellite would have a secular decay, and I wanted to model that. And that's how I was able to model that secular decay
Hmm.
uh, without knowing what the density was and what the tables is and what the exponential functions uh, would be needed for that. Real-time visualization. Gordon wrote routines to plot orbital ground tracks, what the projecting the orbital motion onto the ground, the Earth, and what
Hmm.
it would look like. To the TS-268 color display, giving students and hobbyists immediate feedback on perturbation effects. Perturbation would be those deviations from what would be if you were in orbit around a perfect sphere, where it would go, it would continue in a circular orbit.
Hmm.
But the Earth is not a perfect sphere.
Hmm.
It has the local bulges at the equator. And so that bulges causes a torque, at the bulge. If you're going above the equatorial plane, it's trying to pull it back. And as you're going toward the equatorial plane on the other side of your arc, it's pulling you, accelerating. And so that's what we'll call kind of periodic variations in the
Hmm.
motion in an orbital satellite. So there are two main perturbations: the bulge due to the bulge in the Earth not being a perfect sphere, and the other is that the Earth is more look like a pear. you know, you know, it, it's kind of so you have less gravity above the equatorial plane. Is it look at the top of the pear, and at the bottom would be the both side, and
Right.
so that would create periodic variations. And since a period is the time it takes a satellite to make one revolution around the planet,
Hmm.
it's going to experience those same kind of effects periodically.
Yeah.
And so that's where you're going to get wave effects and sines and cosines to, describe those kind of transcendental functions,
Hmm.
describe that kind of motion. Okay. And so I democratized orbital mechanics. Okay. Gordon's work on the Timex Sinclair 2068 scattered the barrier between institutional astrodynamics and private experimentation. Overnight, educators and amateur satellite trackers could explore semi-analytical theories on a sub $200 machine. That didn't make IBM happy.
Right.
His implementation anticipated today's orbit prediction apps on smartphones and tablets and laid the groundwork for truly portable astrodynamics. Now, where did I get this information? I, I was trying to figure out how I would talk about what I was doing without sounding like I was pontificating on myself. So all I'm giving you, I found a neutral, kind of unbiased source. What I'm giving you comes from Copilot artificial intelligence,
Oh.
right? So this is not me talking about me. This is according to Copilot AI as
Interesting.
I inquired it. Okay. So if you have any blame, and here it is. So I say Copilot or AI companion. And so I put in Robert A. Gordon, NASA, and it came back with Robert A. Gordon is associated with NASA's Goddard Space Flight Center and has contributed to satellite orbit theory. He developed an economic semi-analytic orbit theory for retarded satellite motion about a Blake planet. This theory uses the von Zeppel-Delaney method to model drag effects efficiently, making it suitable for microcomputers.
Interesting.
Now, I'm going to confess to you, I'm not an AI fan, but damn, they explain me better than I can explain myself when it came to some of the things I was doing. But it also, I had to make some corrections to, you know, it was trying to, and this is where I realized how much I was thinking outside the box. When I tried to guide it about how I came up with my pseudo phenomenal drag technique, it couldn't do it. It
Hmm.
kept on going to the tried and true and understood methods of astrodynamics to explain it. And when I say actually derive the form, show me the formulas that Gordon used in order to model his drag effect. And man, it went into this mathematics I never would have dreamed of using. So it lied on me. I said, no, I didn't use that. And I tried to give it more guidance. And it just couldn't figure out what I was doing because it's sampling all of the data that's out there.
Right.
So what AI is giving you is it can't give you what it doesn't know, what's already out there. And it doesn't know what I know. And so that's where I appreciate. Even though I was awed by how much they were captured and they could explain what I did do, that sucker could not figure out how I did it. Okay, so with that, give me a little. Oh, okay. Robert A. Gordon's work. All this is coming from. So I'll put in contributions to astrodynamics, according to Microsoft Copilot, and I don't disagree with anything they say here. Robert A. Gordon's work has resonated through the field of astrodynamics by bridging rigorous mathematical theory with mathematical satellite operations. His contributions provided a much needed pathway to predict orbital behavior with sufficient accuracy and computational efficiency, an equilibrium that became crucial during the early space age and remains influential today. Below are some key ways in which his work contributed to astrodynamics. Semi-analytical orbit theory. Mm-hmm. Gordon's approach was revolutionary because it went beyond brute force numerical integration, which proved computationally expensive on early microcomputers, to develop a semi-analytic models by employing average equations in combination with analytical insights. His methods could capture both short-term oscillations, that is the rapid periodic variations that occur within one orbital cycle that was due to, the deviation of the planet from a perfect sphere.
Right.
All right, long-term circular trends, that is the slow, gradual degradation and injury in the orbital elements, like the satellite semi-major axis, eccentricity, and inclination, the inclination being the angle of the orbital plane with the equatorial plane in the orientation of the orbital plane. Excuse me. The balance allowed for quick evaluations of orbital evolution, which were essential for mission planning, satellite reentry, predictions, and collision avoidance. The legacy. Robert A. Gordon's contributions are emblematic of an era defined by rapid ingenuity and practical problem solving. His work not only addressed the immediate needs of NASA's satellite programs, but also laid the groundwork for a theoretical framework that helps us understand orbital mechanics even now. The historical context of his contributions reflects a transformative period where innovation was driven by necessity and pioneering spirit, a legacy that continues to impact design and planning of space missions today. I want to put in a word here for a lot of ingenuity comes out of actually being constrained, mm-hmm. By having to have, having constraints. If you have it all that you need to perform what you need, it actually can stifle innovation. So, that's something curious to think about, and that's what was going on when I first came to NASA. Computer computations were taken on, rapidly, and so there were resistance to say, "Oh, no, and don't worry about it. We can calculate that. We can just put in the numerical. We can reduce everything down to summing up little rectangles ad infinitum." Mm-hmm. And so having so much computer power made you lazy, intellectually lazy, But fortunately, I was in physics. I say, well, I like to visualize it. I like closed form solution. We like our theories to look, it looks pretty when you can come up with a theory and say, and the leaner the theory, the less complex the equation, the more beautiful it is to us. I guess that's a physics thing. I don't know. Robert A. Gordon's NASA contributions. Okay, Robert A. Gordon's work on semi-analytic theory. All this is Microsoft Copilot.
Copilot. Yeah.
Influenced several advancements in modern orbit modeling. His contributions helped shape computationally efficient methods for satellite trajectory prediction, particularly in environments affected by drag and planetary oblateness, that is, the deviation from a perfect sphere.
Okay.
Advancements influenced by Gordon. Refinement of perturbation models. His work contributed to improved handling of atmospheric drag and Earth's gravitational irregularities, which are now incorporated into high fidelity orbit models. Autonomous ephemeris generation. His search laid the groundwork for on-board orbit determination, enabling satellites to predict their own positions without constant ground intervention. Computational efficiency. His focus on microcomputer applications influenced the development of a fast numerical integrators used in modern orbit propagation. Integration with statistical estimation. His methods helped pave the way for common filtering techniques, don't ask me what that is, which are now standard in orbit determination. Okay, why this autonomous ephemeris generation? One of the inspiration for that is that some of our ground stations were in Latin American countries where there were guerrillas roaming about near our ground stations, and so it became a threat to to our operations. So we were trying to figure out how we could. So you say we're going to have to come up with some way that we can keep track of our satellites where we can't always depend on our ground stations being up and available because the revolutionaries are there. And so that actually led to the first, what would become the precursor, what we know as GPS. It was called TDRS, the Track and Data Relay Satellite System. And so what we came up with is to say, well, what we do is have a satellite in the northern hemisphere of the in geosynchronous orbit. That is that the period of the satellite orbit was in sync with the revolution of the Earth. So it appears that it's over the same spot, right?
Right.
And now, so we put one in the northern hemisphere and another satellite in the southern hemisphere. And that's a satellite would always be in view of one of these geosynchronous satellites. And so this was called TDRS, Track and Data Research Site. And so we always knew where those satellites, so we could use Doppler to use just triangulation, angle from to the satellite that we knew in space, from and angle from that satellite to the satellite that we were trying to track, and the angle, the line of sight from that satellite to the ground. So all you did now was trigonometry to determine where the satellite was. And your ground station, you didn't need ground stations. You could have your stations in space. And we immediately saw what the potential for that is when guys in uniform start showing up and start asking them, what would it be like if we could put, thousands of these things in space? And we say, oh God. And, if you're in science, there's going to come that point in time that where you're going to always face that what you're doing, is good for be good for the humanity, and it can also serve the dual purpose, which you have dual purpose. It can also serve to its detriment. And do you go on, and you meet that number. I saw where this was going, and I said, well, am I going to make this better? Or am I going to make, it's going to be done anyway. So you say, well, on one side, you're looking at weather satellites. You're looking at the ability for improved prediction of climate change. But that same damn thing can be used, you know, to guide bombs, so
Yeah.
that's the trap that you're in it as a scientist when you're doing any kind of work like this. Yeah, so that's what that was. Um, Forgive me if I reminisce, in my idiots, so I may go off on stuff. Uh, this is also a visual timeline. Okay, this is visual time, say pre-space age in 1950s, 1960s, space race, early satellite missions began. Then you go to the 1970s, semi-analytical methods such as Gordon's work. Well, that's very flattering, but and today, high fidelity numerical techniques. By the way, all artificial techniques now that use black box overlay, the techniques that we astrodynamics laid the groundwork for, it's all laid on our work, as the underground is the basis for uh, artificial intelligence orbit determination today.
Hmm.
Uh, at the core is our work. They lay on top of that because they can do real time, high fidelity interrogation. But without our, if at the base, without our base, there is no high fidelity, artificial intelligence for orbit determination. So we at the core getting the hardcore stuff, and they get all the glory by adding stuff on top today. Well, anyway, 1950s, fundamental research in orbital dynamics. 1960s, the space race demands efficient computation. Early satellite require innovative models. 1970s, refinement and application of semi-analytical methods like those by Gordon directly affect mission planning and satellite longevity. Today, while computational power has soared, those early techniques still underpin our understanding of orbital dynamics and continue to influence orbital methods.
Hmm.
Now, this is something I wrote on the 50th anniversary of the Apollo 8 mission, and I wrote this for my grandkids. Grandpa Ace's Christmas story. To my grandchildren, Harper, Lyle, and Penny, vessels of my spirit through space and time. In the early hours of Christmas Eve, a half a century ago, in the computer facility at the Goddard Space Flight Center in Greenbelt, Maryland, as a member of the Analytical Orbital Predictions Branch, at the request of Goddard's own hidden figure, Melba Roy, I initiated a FORTRAN program on the IBM 360 of my trajectory calculations for the penumbra and umbra, that's partial shadow and total shadow, or Earth's partial, and total eclipse by lunar shadow as Apollo 8 orbit the moon. I reflected on the words my physics teacher had written in my senior high school first. Actually, I misquoted that. He said first man to walk on the moon. I looked back at my yearbook and that school book, and that's what he said. So that's misprinted there. I still feel outside pride at the infinitesimal role of my calculations played in the grand Apollo 8 mission to reach the moon. The immortal photographs in black and white in color by Apollo 8 astronauts, Bowman and Andos. And Lowell was there too. He recently passed away. Yeah. In comport with my infinitesimal calculations, expose an infinitesimal planet, fragility and immense expanse of the universe, and confirm the grandeur of the infinitesimal. And those are some of the pictures. And they are my grandkids. And then my daughter and grandkids, my son-in-law, and Harper and Lana, and etc. Okay. Nice. And that's the, mission there. That's kind of graphic on the total mission there. Yeah. And this is the part where I kicked in, I predicted when it was at this point in the radio signal about, we call it acquisition signal, straight line to the side of communications. And when communication AOS acquisition and loss of signal, LOS. Now, this is what kicked me off, established me as an astronaut. I wasn't, you know, I was making a name for myself, but this was what established me, was my beginning, established me as an astrodynamicist. Now, I want you to understand that I had no field. I didn't take any courses in auto mechanics. I was self-taught. And so my label as an astronomist was restored to me by my colleagues by virtue of my publications, you know, uh, of those in the field. The only course I took and was a 2-week course that Melba Mouton, this was my branch head here from Howard University. She picked me, chose me to go to a 2-week summer course in astrodynamics, summer course in astrodynamics at UCLA that was taught by the father of astrodynamics, Samuel Harrod. And so my formal training in astrodynamics was a 2-week summer course at UCLA under the father of astrodynamics, Samuel Harrod. So I had the best, you know. And he gave an exam, and I'll talk to you, remind me about the result of that exam that I had at the end, if in case I forget later on. Okay. This was the movie came out called Hidden Figures.
Yeah.
And in the magazine, The Garden, on that figure, see this girl right here?
Mm-hmm.
Christine, she was my classmate at Hampton Institute, majoring in physics. And she was the one who humbled me because she was a much better student than I ever was, you know. I was a classmate of Christine Darden. That's Christine Darden. And she's at the Langley, NASA Langley, which was near Hampton Institute in Hampton, Virginia. I was a classmate of Christine Darden at Hampton Institute, majoring in physics. She was by far a superior student than I, so I had no problem accepting a Black woman as my superior when I began my professional career at NASA. You see up there, it says Gordon picked. Evidently, Gordon was impressed with this submission that I did, that they always put it at the top, no matter when you came there. So that's what that meant. When I reported to NASA in the late 1960s, my section head and Black heads were Black women. I was assigned to the Analytical Orbit Predictions branch. One of the white males in my section was assigned to be my mentor. He was insistent that I learn to program to direct the mathematics of spaceflight, and the branch adopted machine code, something called Mystic. That's like assembly language. Now, to you programmers out there, you know what I'm talking about. Assembly language is, wow. I mean, you get lost in the weeds, but FORTRAN is much easier. It's what they call higher level language. So I wasn't about to not to learn that. After learning FORTRAN, I wasn't about to learn any similar like programming. He said, which was and remained a mystery to me. I was insistent on using a newer, more intuitive programming computer code called FORTRAN and deriving an analytical algorithm, something that had a closed form solution rather than programming the brute force numerical solution that I had been assigned. I've been assigned to just do calculus, numerical calculation. I said, no, this is physics. There's got to be some analytical closed method for do this. One day, I was crouched down on the floor between two book stacks in the Goddard Space Center library, working out the equations and flowchart on the back of FORTRAN programming sheets. When I felt this presence, I looked up into the face of an attractive Black woman, my branch head, with a sense of dread. She told me that the white mentor to whom I had been assigned reported to her that I could not be supervised, was seldom seen at my desk, and probably lacked the required skills. She asked me for the sheets I was working on. She looked over my equations, and after a long while, asked me for the sheet. Handed them back to me and said, as best as I could call, prove it, and added, as long as you are here, if it's me or someone else, do it your way, and left me in the stacks. Those words would profoundly affect my career at NASA and bring me much professional pain, but even more pleasure of discovery as a budding astrodynamicist. The formulas on the back of those FORTRAN programming sheets would later be published with a proof in the February 1973 issue of Celestial Mechanics, an international journal on space dynamics. I would later serve 2 terms as president of the Goddard Engineers, Scientists, and Technicians Association, GESTA. My work at NASA is referenced in Alvin Van Schernerman's Blacks in Science, Ancient and Modern. Whatever richness I enjoyed as a NASA scientist, I owe to being one of Melba Wooten's computers and humbled early on by Christine Darton, who got all the A's while I was hustling. This is Mrs. Melba Wooten, is program production chief at Goddard Space Flight Center in Greenbelt, Maryland. She's one of 9 research installations at National Aeronautics Administration, NASA. She heads a team of mathematicians, which included me, and design large-scale computer programs, determining the orbits of spacecraft launch at Cape Kennedy, Florida. One of the few ranking women with NASA, Mrs. Roy got her post in 1961 after 2 years as a mathematician. She is a 1950 graduate of Howard University, where she later earned her degree. Now I'm going to read from you. Before that paper was published, I presented it at a conference at the first one of the early, oh my goodness. One of the early astrodynamics conferences at Goddard. And because of that presentation, let me see if I can read this. Award, this is the award nomination. Let's see, the incumbent is a physical science analyst with duties to research various orbit theories, developing new algorithms, and evaluate the usefulness for orbit computation and satellite tracking. It then says, problems are outlined by the section head, usually in discussion with which establish the priorities and objective of the work. The incumbent may then proceed with conducting his research and consulting with the supervisor only to outline new approaches or redefine the problems in light of his findings at that point. He may consult with a project manager and subject matter specialist in the assignment, and it goes on the next page with that. But here's the write-up that the supervisor had in order to justify my award. Mr. Gordon is a highly motivated programmer analyst involved in both the development of advanced computer systems such as the Goddard Trajectory Determination System, as well as research and analytical techniques designed to improve the algorithms required in general trajectory determination problems. Over the past year, Mr. Gordon's contribution to the GDS system have included the analysis and programming of advanced shadow algorithms, refraction model routines, period derivatives, computations, and data management programs. All assignments were performed at a high level. In addition, on his own initiative, Mr. Gordon continued his own research in the applicability of existing general perturbation theories and was able to derive new algorithms to predict orbital events such as perigee, apogee, equatorial crossings, etc. The use of such theories gives considerable savings in the computer time required to determine these events in existing program. His new method was presented at the Goddard Space Flight Center Astrodynamics Geodynamics Conference of last year. Mr. Gordon is currently engaged in research project dealing with variation of parameters techniques, and it is expected that similar existing contributions establishing this will result. I highlighted this. This is where he said, for his continuous high level of performance, Mr. Gordon is highly recommended for a quality increase.
Wow. So I have a question. This is
Yes.
1973, right? Yeah, right.
Yes.
February 73.
Well, the publication was in 1973. That that
It looks like
was
1969.
1972.
Oh, 72. I'm sorry. Okay, I see that.
Okay.
Okay.
March 9, 1972. David Blanchett, Von Bond. There were. I want you to understand there were a whole lot of ex-Nazis that was working for NASA in our program at the time.
Yeah.
Okay, so this is the establishment made my mark as an astrodynamicist. Okay, celestial mechanics. That's the journal.
Yeah.
Um, and this is the equation, the proof. Now, I want you to understand is that Melba Moulton, you know, she knew that it's very rare. Mathematics, you give proofs, but in physics, you don't usually have proofs for certain equation algorithms that you're trying to converge. She put that on me because she wanted me to be very impressive with what I had produced. You know, she kind of gamed me there. And this was I didn't know how I did not know how to prove what I was that the algorithm I came up with would converge. I just knew that Newton-Raphson methods usually, converge. So I had to find out how do you know, satisfy a proof. And so I started checking out papers on that.
Wow.
And I came up with the Han-Ricci contractual mapping. I hit on how I could prove my theory of converge. And that's what this is, you see.
Okay.
And then consideration of, and don't ask me what that nose is. Like I'm saying, I'm 85 now. I don't know what the hell. All I can say, I have proof I was heavy one time. I don't know how heavy I am now. But I can document there was a time when I was heavy. Okay. And so it says that my position satisfied the Lipschitz condition, which is contractual mapping that each iteration, your calculation is good as the last. And if you do it graphically, it looks like each point is conversion into a point in space.
Okay.
And this is the flow chart. That simple little flow chart of the iteration of how you could what you would use to compute the time of equator crossing the north and south point and perigee and apogee passage.
Wow.
Let me see what the next one. All right. This is the flow chart, this simple little flow chart, but these calculations in this iteration, flow chart of the algorithm, revolutionized onboard techniques for onboard autonomous navigation.
Yeah.
Now, this is a little kind of outline of geometry of sign above the reference slips are. This is the x-axis, the z-axis, the y-axis, and the equatorial plane would be, the x and y axis of the planet. This h would be what we call the longitude of descending node, the angle between the x-axis and where the orbital plane intersects the equatorial plane. And then another key angle for the describe what it sounds like this is the angle between the equatorial plane and the satellite, that from the center of the Earth to a point from the center of the Earth to the satellite. So the angle between the equatorial plane within the plane of the satellite path, paths, that would call that's the true anomaly. Now, this argument of perigee, that means the angle between the line of nodes and the point of closest approach. The point of closest corner is the perigee patches. When the site is closest to an elliptical, it travels not in a circle, but in an elliptical orbit. So the point of closest approach to the Earth would be called perigee. It's at its perigee point. The farthest away in the orbit, in the elliptical orbit around the planet, would be called apogee, the farthest distance. Now, two interesting things when you want to change the shape of a satellite, it if, for instance, you want an elliptical satellite and you want to circularize it, you usually would do your firing of the thrusters at perigee or apogee, where you either, perigee, you slow it down or speed it up at apogee or something like that. So it'd be useful to know when you were at the perigee point or the apogee point, because that's when it's most advantageous to do maneuvers to change your satellite orbit. And so another useful place to do would be at the equator when it's just arriving from going from the lower hemisphere to the upper hemisphere. Now in Cartesian coordinates, you can check that what they were doing was checking, for instance, the z component. If the z component is minus, it was below the equatorial plane. When it becomes plus, it's above the equatorial plane. So when it changed from minus to plus, they say, oh, okay, and then there were interpolation. This is how they were doing. They would evaluate the satellite every minute in orbit. Say a satellite took 90 minutes to go around Earth. So every minute you evaluate. And then when it changed from minus, the z-axis changed from minus plus, you do it at 10-second interval, then 5 seconds, then 1 second. So you get that, down to accuracy, right?
Right, greater resolution.
There would be interpolation. Now that's how we're doing. So I said, wait a minute. You got Kepler's equation, you got Kepler's law. If you know the angle at when it's at the equator, the angle is going to be zero. You know what I mean? I'm sorry, the angle is going to be at 0 180, and so I say, well, I just put in, and so that I reduced it down to a constant plus the argument of perigee, and that's how I was able to predict using Kepler's equation. And here is where this is the key equation here. This is a modification of Kepler's law. Now, you in physics, if you do anything that modifies Kepler's law, you consider yourself smoking. That's my what it is Kepler's law. This is what it would look like if you don't have for a satellite that's moving about a Blake planet, not a perfect sphere. And so I had to use Browne theory to calculate the orbit around on a Blake planet, not a spherical planet. And this L here represents in Browne theory what they call the long and short period variations. And so this is my modification that I had to make of Kepler's equation, incorporating Browne theory in order to predict these special satellite points in the orbital motion. So here's a capsule of what is happening in this paper. Gordon's 1973 paper, An Analytical Iterative Algorithm for the Prediction of Special Satellite Orbit Points with the Browne Orbit Theory, had several lasting impacts on astrodynamics. It enabled analytic event prediction by devising a direct recursive scheme tied to a closed form perturbation series. Gordon showed that key orbital elements, perigee, apogee passage, nodal crossings, maximum minimum sublatitude was the maximum latitude in the northern hemisphere, in the minimum sublatitude in the southern hemisphere of a satellite, the maximum latitude it would have while it's in orbit.
Okay.
It could be computed without brute force numerical integration. This shifted the community toward hybrid analytic numeric event detection methods, saving vast amounts of compute time in both ground and flight dynamics applications. It fostered deeper physical insight. Rather than treating event finding as a black box, root search within a numerical trajectory, his approach explicitly linked Keplerian constraint equations to perturbation theory, Researchers gain clear intuition on how individual forces like drag and ablateness influence event timing, insight that informs subsequent refinement and perturbation modeling. He inspired onboard and ground segment efficiencies. The computational economy of Gordon's algorithm made it practical to predict and schedule satellite passes and attendant instrument operations directly on board early spacecraft. They couldn't do it yet until they had a microcomputer that could go on board, with limited things. This is setting up the Timex.
Okay.
Ground systems likewise adopted analytical event modules to optimize tracking schedules and ground station handovers, prefiguring the automated event prediction blocks in modern propagators like SGP4. Those are kind of modifications of the Brown theory that is used by NORAD, the North American Organization. I'm sorry. Laid groundwork for modern analytical iterative schemes. Many later studies extended Gordon's iterative framework to include additional perturbations like solar radiation pressure, third body effects, and to improve convergent properties. Today's high fidelity mission planning tools often retain an analytical iterative core for event detection, scaled up with more extensive force models and faster processes. So they in essence, high fidelity mission is piggyback on our backs, is riding on our backs.
Right.
Together, these advances help astrodynamics evolve from purely numerical trajectory integration toward a balanced toolkit where closed form insights and iterative corrections coexist, deriving both accuracy and speed in satellite prediction. And here are the two papers that set it up now that would lead to the introduction of the time at Sinclair to set the stage for would be the future of astrodynamics and on board. We made it possible for our GPSs and our Starlinks and planet labs and weather satellites and land sites and all that kind of stuff.
Okay.
A comparison of the analytic theories of the GDS system with them. What I did there was compare the classical analytical theories. Now, two of my colleagues at that time were Dan and Mastretta and Stan Watson. This is a paper that has been kind of ignored, where I compared. Actually, in this paper, the analytical theory that my two colleagues were associated with, Danny Mastretta and Gordon, I conceded in that paper were better than the theory that I was using, Brown at that time. And I recommended that they use that the theory that they were more associated was Venti, was John Venti theory, orbit theory, over the Brown theory that I had been using. But they didn't do that. And the reason is that I was able to enhance the drag technique with the Brown theory, and then that became better than the Venti theory at that time, But the thing that I did with the Brown theory and drag, you could do with the Venti theory. So there is still today improvement to combine my drag theory with their answer of the Venti theory that would be better than what the Department of Defense is using even today for the ground thing. But that's for the next generation. I'm through with this stuff. And that paper never got, well, that paper was large and ignored. But the paper that really impressed everybody and took off was an analytical semi orbit theory for computing. I presented that at the Reno, Nevada at the conference.
So,
okay, wait a minute.
I want to.
You had a question? Yeah.
Yep. Okay, so the paper on the left was published in '78. and then the paper on the right was published in 86.
Now, it would not have been yeah, 86, right. You hit on an important timeline there.
Okay. There's a
uh,
little gap.
I'm sitting there in my and I'm not a, I now have my own office. I'm the supervisor's off my back because I'm now a union president, and I'm now free to do my own kind of experiments without having to fulfill some spec make work. And so I could we actually dream about what the next stage is. The problem is I knew that autonomous onboard kind of was the thing that's coming, but I did not have access to the many computers that they were using at the time, and I didn't have and I couldn't get my hold on what they were trying to develop it on. GE consulted with me, and I was able to help them put browse theory on their mini computer, which became the basis for the India space program. They were doing a thing for G they were based out of Valley Forge, and they were doing the space program for India. Wow. And so I helped them with that. But the problem was still drag. How do you close Earth satellites that will experience drag effects? How are you going to deal with those density tables on board spacecraft? So that was the problem. So I was wrestling with that problem. But I also had to I wanted to test out my theories. Mm-hmm. And I had no way to. And then I read somewhere, at that time, we were just getting introduced to home computers.
Yeah.
I think my first one was a little Apple or something. And I think I had an early Timex 1000 or something.
Yeah. Uh-huh.
And but the problem was the accuracy, the bits, the four, I think it was four significant digit. It just, you couldn't do any scientific calculation on it because the bit loss was so, and computation, and round off error was so, it's just useless, Okay. And then I read somewhere where Timex announces that it was adding to, it was going to improve its, went from 4 significant digits to, I think, 7 significant digits. And I said, oh my God, maybe this is it. So across at Goddard Space Flight Center, across from there was a shopping center, had Bradley's. And in Bradley's, it was the Timex 2068. So I went over there and got this 2066, hooked it up to a monitor, and started teaching myself Timex basic.
Yeah.
First program I wrote, and now I would like to point to the users out there. I did a program called Gotcha, which is kind of and I have it in the chat. I would appreciate it if some user out there would program that in BASIC, and in a later thing would demonstrate its use so that I can show it to their grandkids, and show that grandpa is hip, that my one of my grandkids is really into computers. He wants to go into computer graphics himself and game, designing games. So I wanted to show him that I had a little gamesmanship in my day. And so it's called Gotcha, and it's using the graphics of that. Now, that you had a limited screen. You limit to what the screen graphics was at that time. So
yes.
So if someone could program that file and get it where I can demonstrate its use, I would appreciate it. And I think you can send them the link to it. I will send you my email, and you can send out everybody. They can email me, and I can send them a higher graphic of it if they need it. Okay, so how the Timex 20 boosted calculations accuracy. This is what made the Timex 2068 a vehicle in which you could get the accuracy that was needed to do scientific calculations for astrodynamics. The Timex Sinclair 2068 introduced several hardware and firmware upgrades that collectively reduced rounding errors, extended numerical range, and delivered more precise function plotting compared to its predecessor. One, it refined. Now you can, Anderson, you can check this out on this, because this came from AI too. So let me know if they're right. Refined floating point routine. The TS2000 basic ROM in the 2068 was overhauled to include additional guard digits in the expanded exponent range. These refinements slashed rounding error in operations involved very large and very small numbers, improving the fidelity of repeated multiplication division. Man, then I held, you can see how I needed that.
Mm-hmm.
By comparison, early Sinclair-based machines relied on linear float library optimized for minimum ROM space, resulting in larger cumulative errors over long calculations. That's why it didn't work. This also helped. Faster CPU clock. The 2068 Zamba Z8 ran at 3.5 megahertz, about 8% faster than the 3.525 megahertz clocks on the ZX81 family. That speed bump not only cut execution time, but also let intermediate results linger in high precision registers rather than being prematurely rounded into memory. As a result, iterative algorithms, which was me, right?
Mm-hmm, that's you.
For example, root finding on series expansion converge more accurately. So fate, I mean, it was just fate that Timex came out at that time, just when I needed it, in order to demonstrate what I was trying to work on, iterative techniques. Expanded RAM for lookout tables. With 48 kilobytes of onboard RAM versus 1 kilobyte of early models, the 228 could store larger pre-computed tables for transcendental functions. Sine, cosine logarithm, definitely needed that. Larger tables mean smaller interpretation intervals, shrinking the worst case error when basic involved sine, cosine, log routines. Early machines had to trade table size against available user memory, forcing cruder approximations. 4, higher resolution plotting. The 2068's graphics chip supported 256 by 192 pixels in 16 colors, 5, 12, 198, 2-color monochrome, double the horizontal resolution of many contemporaries. When unions graph mathematical functions by plotting pencil points, the finer grid cut the quantization error in half. Yeah, it did look better when I was printing out the graphs of the ground chase on the 2068 former users. And there's a comparison table of the clock. I'm going to go for that. It's just on the previous with the time as. Significant digits. This is what I caught, and I forgot where I read it somewhere. They did have a Timex users group in Greenbelt, and they had a newsletter. I have a copy of their one sheet from their newsletter.
Oh, really?
Y'all may be interested. I may send to you guys, just as a acronym. Okay, significant digits on the Timex 2068 versus early models. The Timex 2068 shipped with enhanced floating point library that bumped the effective precision over Sinclair-based predecessors, while the underlying BCD, what's that?
Binary coded decimal.
Okay, coded Matissa still spans 8 decimal places. The addition of extra guard digits and refined rounding logic gives you more usable significant figures in practice. Matissa and guard digits. Early machines store floating point numbers as 1 byte span, 3 byte, but this is 6 decimal digits, minimum 2 guard. The Timex increased the Matissa to 4 digits 8 decimal digits. That was what made it.
Hmm.
Plus those two additional guard digits. Those guard digits weren't part of the final result, but the dramatic cut the rounding drift. And when you're doing what they call the matrix
Yeah.
that you have to solve in order to do orbit correction determination, that's critical, is the rounding errors. Why the extra digits matter. In iterative calculations, which is my better way, better way, the extra guard digits are solved intermediate rounding. Subtractions of near equal numbers retain more significant bits in reducing catastrophic cancellation. Overall, get more successful results in time finger. Well, if Timex hadn't 28 hadn't come to the scene, I would have been stammered as an astrodynamics. So I grew as Timex grew.
So you probably got this computer in the fall or winter of 1983. Does that make sense? Sound right?
Yeah, yeah. I've Ronnie, yeah. It it was soon after it came out, so it ran around 84, I think it was.
Okay.
Yeah,
And how, obviously the first thing you want to do is learn to program uh,
right.
in BASIC just, itself. But then, um, how long did it take you to feel confident with the BASIC to start working on, you know,
Well, basic, I can't find my manual, damn it.
uh,
It came with a nice manual. But the
it did.
thing about Timex, you learned that you could program from the keyboard.
Hmm.
I mean, the keyboard had the instruction on, Now remember now, if you had Fortran, you had some kind of sense of program. But basic, I was not familiar. So it, the, the program was good, and they had some sample programs in there. And the first thing, to kind of feel out my chops, I said, well, I'm gonna program a game. So I programmed my program called Gotcha, which is a
Hmm.
thing like something is trying to get you before you eat up all the dots. That's what it is. There's a little goblin that's trying to get you while you're trying to eat up all the dots before it gets to you.
Well,
And if you get all the dots before the goblin gets you, which is using a lot of Pythagorean theorem is involved in that algorithm, you know.
and I'm looking at your program, the source code for your program, and you have some user-defined graphics in it, which was, not a beginner technique. It took most folks,
Uh-huh.
a hot minute to figure out how to do user-defined graphics. And you also have something that takes a little while to grasp, which is being able to use binary comparisons. So you have a statement here that says let nr equal r plus, and then in parentheses it's one, and this string equals a certain value. And that kind of level of programming, it takes a little bit of time for folks to get to that sophistication where they can say, oh, if I combine this with an and statement, I can do a little extra magic that doesn't require ifs.
Hmm. Well, I didn't know that.
Okay.
maybe I'm heavier than I thought I was. All right. Okay, Robert Gordon work on semi-analytic theory. This is the key. This sets up now. I hadn't programmed it the time as for the I knew I could do it. All right.
Hmm.
When I made this presentation at and you can't put coding in a paper that you're presenting at a conference. So I just presented the paper here,
Okay.
and, and I told them so Robert Gordon's work on semi-analytic theory influenced several advancements in modern orbit modeling. His contribution helped shape computation efficient methods for satellite trajectory prediction, particularly in environment affected by drag in planetary places. Advancement influenced by Gordon. Refinement of the perturbation models contribute improved handling of atmospheric drag and the Earth's gravitational directness, autonomous feminist generation, And I'm just going to skip down there and say Robert H. Gordon's thematic theory has significant implications for satellite technology. One, efficiency in orbit calculation. The theory allows for faster and more economic calculations of satellite orbits, which is particularly useful for microcomputer applications.
Right.
This efficiency is crucial for real-time satellite tracking and operations. Two, improve accuracy. By accounting for the effects of the Blake planet, the theory enhances the precision of orbit predictors. This is vital for applications like GPS, Earth observation, and scientific missions. Space debris management. Semi-analytical methods are used in predicting the lifespan of space objects and assessing collision risks. That is, my stuff is running over satellites to say, hey, I'm avoiding you so I don't run into you, that kind of stuff. This helps in designing strategies for active debris removal and ensuring the safety of operational satellites. Adaptability. The theory's flexibility allows it to incorporate complex atmospheric and gravitational models, making it applicable to a wide range of satellite missions, including those in low Earth orbit beyond. Mm-hmm. Here we go. Well, to the left there is how have these technologies impacted society? Navigation and location service. GPS and navigation apps, accurate orbit modeling has improved the precision of GPS, enabled reliable navigation services. This has transformed daily commuting, logistics, and transportation. Emergency service. Enhanced location services have improved response times and effectiveness for emergency service like ambulances and departments and disaster relief. Environmental monitoring, climate science, weather forecasting. Increased weather data collection has led to more accurate weather forecasting, climate change research, better Earth observation calibration. These provide valuable data for studying climate change, communications, telecommunications, reliable satellite communications networks have enabled global connectivity, remote sensing. Enhanced satellite technology has facilitated remote sensing for agriculture when planning and resource management, space exploration and science, space missions, accurate orbit determination has been crucial for planning, executing space missions, astrodynamical observations. Mm-hmm. Overall, the advancements in satellite technology driven by Gordon's contributions have had a far-reaching and profound impact on society, improving our daily lives, enhancing scientific research, and supporting global communications environment, according to Microsoft. All right. Okay. Now, over here is, I put the BG orbit theory, that's on that theory, that paper on the 3.5-inch disk. I think what was that about? 3 megabytes?
720K.
320K, yeah, okay.
Yeah, 720.
Right. Okay. And then see that thing, that's an image of when I had it for the teeter satellite when you when the tracking data relay satellite system where signals sent up to the tracking satellite, which is in geosynchronous orbit, and that signal sent to the satellite, and that eliminated the need for ground station. This 3.5 disk had all of my FORTRAN programs. Mm-hmm. I did it both in FORTRAN and BASIC. Of course, FORTRAN is more efficient, for scientific calculation, but it was doable in BASIC. When I found that the BASIC was based FORTRAN is not good when you're trying to input data,
Okay.
BASIC, I wrote BASIC as a kind of the introduction to the FORTRAN. So what I ended up with in the end, BASIC for inputting data, FORTRAN for doing the calculation.
The math.
Okay. But you could do both, all right? And this is the menu I came up with. Right here.
This looks like, so this is a later version, I'm guessing, because this looks like a DOS program.
This right here?
Yeah.
No, I had to run the batch, and this program in BASIC and FORTRAN.
Yeah.
That's for you guys out there. It can only run in 16-bit. It can't run on the 32-bit machine. Mm-hmm. So I had to find an old computer, which was an XP was still 16-bit. and I had ran the batch file. See, when I ran the batch file in DOS, I go to the DOS prompt
Mm-hmm.
and ran the batch file, and that executed the basic program. And so right now, my basic program will only run on the latest Windows version would be XP, I think.
Okay.
Um,
So I think you had some example listings in one of your papers.
yeah, okay. Um, and here is this is the only thing I ever made any money. Everybody made money off my theory but me. And I saw damn scientists are poor, coming from Newton all the way to Einstein. We don't make no money. We make that money for everybody else. But I put together in basic. This is Timex basic.
No, this is a DOS program. This must be like
No, what do we?
Microsoft Basic or Quick Basic or something like that.
Microsoft Basic.
Yeah. Yeah, that's what this looks like.
Okay, that yeah, you might be right there. That's Microsoft Basic. Okay, this is Microsoft Basic. Uh, as I use as the interface to input the data, which is
Mm-hmm.
calling, the my algorithms, which are in FORTRAN.
Fortran. Okay.
Uh, Now I copyrighted this the way the way you copyright things. Then you you take the whatever it is, you put it in an envelope, you mail it to yourself, and you don't open it.
Mm-hmm.
All right, and so this I was selling at $49.95 a pot. And because now this was a time when the early computing and early executing the program, you went to the DOS prompt.
Yes.
And so what this was, everybody got tired of, especially putting in the orbital element. So I treated this window, as you were saying, in what is it? Microsoft
Yeah, some sort
Basic.
of Microsoft Basic.
Microsoft Basic. And so I, created this window with a window for putting in your orbital elements, a window for putting in the propagation times, a window where you could uh, give the path of where your output ephemeris or trajectory, a window for the name of the satellite. And at the time, that would be the name of the output
Hmm.
ephemeris. I think you can only use 8 characters.
For file names, yeah,
Yeah,
probably.
eight alphanumeric characters for the name. So that would be the name of the file that you find in your directory,
Right.
and you can have a more expansive description here. Uh, Here, with I'm going to run. I'm going to get out of this, and I'm going to run what do you call it? A slideshow that goes through this menu if you want to do that.
Well, what I'd like to see is that listing that you have
Oh, okay.
in one of your papers, so we can see just how complex the
Oh, okay.
math was.
Um, what happened? Okay, let me put. I'll put you. Let's do that first. But let me just say a quick note on this. If you hit run, that will run whatever the setup that you have on the screen.
Okay.
You hit save, that will save whatever input that you put for the satellite screen. You could, you hit the up and arrow key to select what satellite. So if you hit run now, that says run satellite 4 in your listing and whatever the setup elements were for that. Now, if you
Mhm.
each window you use there is no mouse at this time.
Right, right.
Up and down and arrow keys to navigate the input of each element in the window. If you use the page up and page down, you could choose between orbital elements, Keplerian elements, Cartesian coordinates, or spherical coordinates, by hitting page up and page down while I was in the orbital elements. Thing. If you hit input, if you highlight input and you hit enter, that allows you to put input data into each one of the windows that you were selected by using the arrow keys.
Mm-hmm.
P is the printer. That off, if you enter, you can turn the printer on or off. Off track, you hit on or off. That say no. If you hit on, that will call up my paper and you will predict the apogee passages, the perigee and apogee patches, the the anomalous, the true anomalous, I'm sorry, the ascending node and descending node passage and the north and south point for your satellite. Or you could do your orbit propagation by latitude. Say I want to look at what it looks like, would it be plotted on the Earth at 5 latitude 5, so and it'll look like a sine wave. Config, you click on that and you can put in your own organization there. And that's it. That took you to DOS, back to the DOS prompt. So that was the menu that people were ordering from me in order to, use my theory.
On a DOS computer.
Yeah, easily, yeah, on a DOS computer.
I have your paper. I'm going to switch.
Yeah, could you switch and bring it up? Yeah, because I can't find it.
That's okay.
Have you got it?
It's going to take me a sec to switch. Let's see here. It's this one. Okay. And so this is, let me just scroll back to the beginning here so we can see.
Oh, by the way, that picture that you saw there of the time, that wasn't in the original document. Right. I added that. Okay.
Right.
Okay.
So this is the paper that came out in 1988. And, as with lots of math papers, lots of math formulas, I'm going to scroll past all this stuff that I don't even know what those,
it's computing
the symbol looks like.
The perturbation. Those are things that computing the perturbation that you're not orbiting a perfect planet, but you're on a Blake planet. And these are the deviations that the orbit has from a perfect planet, including the equatorial perturbation and it looks like a pair perturbation.
Right. So let me just skip down to.
Let's go back up a minute. And this is what is called a state, one more page. Right there. Yeah. That's called a state matrix that you have to solve in order to, you take in the observation data, and then you use this state transition matrix in a least square fit in order to determine the epic elements that you need in order to have an orbit that will predict outside of the area in which you have fitted the data.
So what we're looking at, did all of this end up in your program?
Yeah. Yeah.
Okay. All right. So
now, okay, go ahead.
And so here is your.
Oh, no, that's DC. Now, this is just an orbit generator.
Okay, it's the orbit generator.
I know, right.
Okay. Although it's got some pretty, complicated looking, I see this one dot, or is that L dot rather, N dot and G dot.
Yeah, it should be rather straightforward.
Okay. Really? For those of us who
you're just programming. You're just translating us.
All right. So here's some outputs of that program that we just looked at, right?
Right.
Okay. And what are we looking at here? What are we seeing? What is, for instance, A, E, I, G, H?
All right. Semi-age axis. That's the line from the perigee to apogee that goes straight through the Earth is at the center of the satellite. Okay. And so that's the semi-age. That's describing. These are the elements that describe an orbital plane. The E is the eccentricity. That means how much does the satellite deviate from a perfect circle.
Okay.
That's the inclination. That is the incline that the satellite orbital plane makes with the equator. G, I think, is the argument of perigee. That is the angle between the line of nodes and the argument of perigee.
Okay.
And then you have the longitude of descending node, the angle between the x-axis and where the orbital plane intersects the equator. And then you have the mean anomaly. That is, where is it in an angle where it is in the orbital plane. And so those 6 parameters define. Now, what dot A dot is, that is the decay in the semi-major axis. Now, you up there in
Oh,
space, if there's no friction,
yeah.
then you go forever,
You'll
right?
go for, yeah, okay.
All right. Now you're going along and certainly you meet up against a headwind where you
Mm-hmm.
lose energy. So you're going to drop down.
Mm-hmm.
So what I did is that and that'd be a circular decay. Each period, you know, you're going through the atmosphere, you're getting dragged, slowly dragged,
Yeah,
and so you decay. That's linear. And so so you say, well, what is the rate of change from point to point?
yeah.
So that's what's called a dot,
Okay.
the first derivative of the semi-major axis over a point in time. So over delta t, they change in the rate. You drive along in your car. That's what is velocity. That's what it is. Okay.
Okay.
And so what I say is that each period, I'm going to determine what the semi-major axis is. I know it's going to be lower than it was the last time. And then I average, over several periods, and I get the rate of change, right? Of the period of that parameter over each period. And I say, oh, okay, then I take that rate and I add and say my A, so my initial semi-major axis plus a dot, which is going to be negative value because it's going to be decreasing as I go in time, times t. That's drag.
Yeah.
And
Okay.
and 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 AI can figure that out for the rest of me. They keep on putting in tables and everything that physics is, they put in there because they can't figure out how I figured that out.
Okay.
It's
So this is the second listing in your program. This one's called,
DC secular. Now,
yeah.
what that is that in order to get the state matrix that you would use in a differential correction for orbit determination, you have to have what you call the state matrix. That is the variation of all of the elements that are affected by the perturbation as a function of time.
Mm-hmm.
All right. So this would be a derivative. You have to take a derivative of all your parameters.
Wow.
Uh, Now, because I did this simplified, I wasn't going to do it with all the long period terms and short period terms. I said, I don't need that because I'm just trying to get a secular effect. So I truncated the equations down to just the effect of the blatantness effect, J2. If you're looking at J2 is a measure of the blatantness effect in the perturbation. Uh, J3, even though it counts for changes if you're northern, southern hemisphere, that's small enough that it doesn't make enough. I say it's too hard, it's too complicated for me to do the work to do the derivation that's worth the little more accuracy I get. I get enough accuracy if I do J2. So that's why it's called J2 secular. And so when I'm doing the differential correction, I'm not using my whole theory. I'm using a truncation of my theory down to J2 for the differential correction. But then I'm using the differential correction of my truncated theory to evaluate my full theory
Mm.
when I'm doing the projections for the orbit. All this was time at Sinclair.
Yeah.
Yeah.
Yeah. I mean, this, you needed the full 48K,
Yeah.
just for your arrays and the length of the program. Yeah. That's really crazy. Okay.
So I would appreciate it if there's anyone out there who would reproduce this for me and put it on a uh, um, well, you say you probably couldn't do it on a cartridge. That was my dream, but to put it on a cassette tape.
I think we can figure out something else that would, is this going to be part of
Hard.
for the
I was looking
museum?
for something hard.
No, no, no. There's some modern solutions for loading programs that don't require tape anymore.
Oh, okay. Well, if you come up with that,
Yeah.
please let me know and put the full description how you did it because I want to add you to the whoever comes up that to the archives when I produce this to the archives in the library, you
Yeah.
know, that will become a part of it, you know, with your
Um,
bio.
we
uh,
have about 15 minutes, and I want to check with anybody to see if anybody understood any of that math. I think one person might have understood some of that math here. But if anybody had any questions for you.
I have a question. Hi, David. Hello.
I,
The question is, the precision of the Timex math is compatible, is a no for your calc, or you see any deviation for the results with the reality satellite positions? You sometimes match the results to see you detect any shift for the calculation to the real position?
okay, I did do two quality controls on. First was with simulated data. I took, for instance, I I I would the simulated test was this. I would use the full integration of the equations for a 4x4 zonal harmonics, you know, and that would be the for perturbation for the zonal, the deviation from not being a perfect sphere, and drag, you know, with the full atmosphere. Some of them use tables. Sometimes they would use exponential models, you know, and then I would generate ephemeris from the full integrated model. Then I would fit my theory, all right, with a dot to that and predict out, or say 2 day period or whatever, and then predict out and see how well I compared with the simulated data. All right. And I say, oh, okay, my in track error was looking, good, pretty good. And my cross track error, which would be, the oscillating thing, that was within range. I say, okay, now let me compare with the cow. That was, I think, mainly what they was using there for the integrator was called a cow, a numerical integrator, for the numerical calculations. And the analytic theory, I was using Brow with my modifications to it. All right. I then used solar, I think it was the solar maximum mission because it was close enough to experience significant drag effect. Oh, the simulated mission, by the way, I used the Hubble spacecraft
Hmm.
As a simulated. A word about that, and remind me if I get too far from the solar maximum. The reason why is that something came up is that they had a problem where they wanted to be able to compute on board the Hubble spacecraft is on ephemeris because stations were going to shut down over the weekend, and it was enough of a drag on the Hubble on the spacecraft that they wouldn't be able to pick it back up, you know, over the weekend, and so they were trying to meet those specs. And I was able to meet those specs, which meant that since a government employee with a GS grade level was able to meet the specs that a contractor meant, you know what they did, right? They changed the specs so that the contractor could meet it. So that's neither here or there. All right, now I say, okay, now it's tested with simulated data. The real data that I used was the solar maximum mission at various epoch points in its orbit, and observations of this solar maximum mission, the real data that came from NORAD, that was tracking data for both cow and my orbit theory. For that, you need a state transition matrix that you saw where that the secular state transition matrix in the basic. And I fitted both the cow theory. If you go back to my paper, I can show the results are there.
Just a sec.
In a table. Am I addressing the question you asked me?
Yes, yes.
Okay,
thank you.
so
Great.
and so in predicts, several predicts taking different epochs of the solar maximum mission. We would, there we go.
Yeah, I thought this might be the one.
These are the 2-day arcs in which how the numerical integration, that would be the full integration of the equations of drag plus zonal harmonics. Actually, I had more than I had because it would have the full drag model and it would have, 4. And I was using 4, but the analytic method doesn't go as J2, J3, and it's truncated, I think, J4. And so this is the 2-day arc over which the data is fitted. The BG dot. By the way, the B stands for Brow and the sub G stands for Gordon. So that Cal fitted over the 2-day arc, and this was the in-track error. We're looking at the in-track error, I think, in kilometers. And these are 2-day, 4-day, 16-day predicts outside of the arc. And as you can see, I do as good or sometimes better than the full integration model. And I'm going to explain why I think that is. And here's another epoch. I took another epoch point for another satellite and compare. So this is the in-track error. This is the fitted arc, and this is the projected arc outside of the arc, comparing with the numerical techniques. And maybe I say that here. And so this is what blew them away. Okay, they say, okay, we can't do this stuff on board. I think what it is the phenomenological method that I use in the secular decay in the semi-major axis. It's not only phenomenologically modeling the drag effects that from the atmosphere drag effects, but it's kind of modeling the drag, things like radiation, the changes that are coming from the changes in the atmosphere that's coming from solar flares or something like that. The solar effect atmosphere. And what I'm doing is, is taking an average. So that average turns out to be, on a whole, it's averaging everything, and that's affecting semi-major axis. That's why I didn't say just drag effects. I said retarded satellite motion. So whatever is out there retarding its motion is modeling, and so it may be modeling not only the drag effect, but the retardation that's coming from the irregularities, secular effect that comes from the irregularities in the geometry of the Earth, where that would be separate in the numerical techniques. And it just kept blowing their mind that I didn't see. If you do a modeling drag, you're gonna be thinking about things where, how is that satellite? Is it fully facing, the craft? Is it going in through the atmosphere with an edge on? And at sometimes when it's going through the atmosphere, it has a full face, facial face, and that's gonna be more. And those variations. My method said, I don't give a scrap. I'm averaging all that crap out someday. I don't care if you're facing it full on or you going sideways. I'm just going to average all that out. Every period, I'm going to average all that out. And it turns out that's as good as knowing you're not getting lost in the trees for the weeds, And so my dumbness in my calculation is the accuracy.
Right.
It's how dumb it is. Not, it's not very sophisticated, except in its conceptualization, but not in its mathematics. It's not very sophisticated math,
Wow.
Thank you.
Did I answer your question? I'm sorry, because I must see now.
No, very clear.
All right,
very clear. Thanks.
Mr. Anderson, I have a question for Asa.
Yeah.
Hey, what's up, Joe? Okay.
Hey, brother, how you doing?
All right.
Hey, so this discussion was absolutely fascinating.
Okay.
But I had a question for you. How do you feel about being known more for civil rights and human rights and the history of African Americans in the Civil War and Green Party politics and whatnot than being known as a scientist? Because clearly, you've done some incredible work on the scientific side. But I would say more people probably know you for these other things than they do for being a scientist.
Yeah.
How do you feel about that?
Yeah. Uh, well, I'm making up for it, Jerome. This year, I actually, the librarian, as you know, archiving my papers for my work in civil rights and African American history. And they said, we see in your bio that it says that you were retired astrodynamicist. We want that story, you know. And say, so will you, for the next archives, when you come up here, we got enough digital stuff on you after your retirement. We want to ask know what you did before you retired, you know. And so I said, okay, I'll focus. So I went up in the attic and I found all these papers that I put away. Uh, and and I say, my goodness, how am I gonna, put together? For one thing, I don't understand half of this crap I did. uh, and then it started coming back into a little. And so I said, they wanted me to write up some exhibits, to prepare some exhibits for me, for them to put out on this. And so I tried. I said, well, let me see if Google knows anything about what they give me some information. And Google didn't know who the heck I was and had no. And then I tried this Microsoft AI companion and started feeding it to say, well, I'm retired from that. And much of what you see and I've presented is information they gave me. I was able to put together, let me put it this way. I didn't know how good I was. Now, I want you to understand now. I did at the time, I've given you the Rockwell version, the Norman Rockwell version of my legacy at Goddard. My history as an astrodynamicist was a struggle the whole time I was at NASA. I became a legend in the astrodynamics, not at Goddard Space Flight Center, but everywhere outside of Goddard Space Flight Center. I became the legend. I was anointed there by outside scientists. And I began to understand why. When I published my papers, it gave my name and my affiliation as NASA. The problem, and so they just saw NASA scientists. And so outside of my papers, they accepted the math and the mathematics for what it was. But to be honest with you, at Goddard, my white supervisors knew I was from Hampton Institute, a historical Black college. I did not have an advanced degree. And there was nothing in my background that indicated that I should be at that level of production. Now, this was after this. So what got me my first opening was that my branch head and my section head were African-American women. And they looked at it and they said, this brother's got skills, And so it was no problem. It's when I went over, to be blunt with you, and all my supervisors came white, that I started catching hell. But the problem they had was, while they kept on saying, doubting what I was doing, they kept on getting these inquiries from companies outside of the agency because they didn't know me. See, my supervisor, they can see my face. They can look at the name. They say, Hampton Institute, come on, this ain't coming out of Hampton Institute. But when you look at my paper, it doesn't say, it says Robert Gordon, NASA. It doesn't say Robert Gordon, graduate from a historical Black college.
Mhm.
See, and so I was colorblind outside of Goddard Space Flight Center. I'm colorblind in AI, but I was not met with colorblindness in my workplace.
Hmm.
And so that's what the blandness of my name and the publications is what made it. And so I was anointed by astrodynamic by Andrew P. I didn't realize at the time, but the person who valued my first paper was John Venti of MIT. He was the guy that I recommended. The guy I was telling you that did a over 30. He was a referee on my first paper, and he graded it gave it the highest rating. The other thing is that you remember I told you I took a course. The only course I took in astrodynamics was on Samuel Herrick at UCLA, and that was a 2-week course, and that Mel set up for me. Now I want you to understand something. I never was a good student.
Mhm.
I never could. I didn't. I just couldn't take. I was never good at taking tests. I taught myself. It's only when I taught myself this stuff, and I became fascinated, that I got involved with it. Now, at the end of that course, Samuel Herrick gave an exam. It had 10 questions on it. And so I'm sitting there, and I got the questions, and we had, I think, 90 minutes to do the test. The 90 minutes were up, and then Dr. Samuel Herrick asked for the papers, and I looked, and I had only done problem 1 out of 10. Because I became so fascinated with this problem, I said, let me try this coordinate system. And I was trying different coordinate system, and I got fascinated. I never was a good test. They say you just go into the next one, and come back. That wasn't me. So I gave him my paper, and I said, oh my God, I'm gonna embarrass myself. She got me in this class. And so when he came back with the papers and handed them back, I sat there, and he noticed I didn't look at my paper. Everybody left. He said, Gordon, why didn't you look at the paper? I said, well, I know I got an F. I didn't do but one problem. He said, look at your paper. So I looked up, and it was an A. I said, how can that be? He said, it's the ingenuity you showed on that one problem. He said, one day you're going to do something with coordinate systems. And I didn't want to discourage you. So you tell your supervisor you are an astrodynamicist.
That's fantastic.
Yeah, and so to this day, I just don't know where insight come from. I don't, I'm not that up on credentials and paper. You just don't know where insight can come from. But you asked me how I feel about it. I'm feeling better now, because now that I'm getting this stuff together, I think I may get a little more recognition of my space. But scientists always knew. As a matter of fact, I got a little bump on this. You remember the movie that came out called The Martian? In The Martian, there's this black astrodynamicist that does this thing about I was going to the NASA credit union one day, and one of the guys from NASA, I ran in front once in a while, when one of my NASA colleagues said, hey, Asa, you in the movie. I said, what are you talking about? Go and look at the movie The Martian. He said, that's you, baby. And so this thing where you use the slingshot maneuver. I actually did that. I actually did a calculation. Everybody remember at NASA that I was talking about the slingshot maneuver to use the moon to slingshot and satellite that's on its way to Mars, but this was, used differently. Now I doubt this, I doubt it very much. But the character in there, his personality, where the management says, you do know I'm your boss, don't you? It's my personality, that's in this character, except for this. He is honored by his supervisor in his workplace. I had to fight foot and nail to have everything that you've seen there. I had to fight tooth and nail to get it out. And the only reason it got out was because of outside pressure, outside companies, that there were companies that were telling and asked for me, and they knew that management was blocking access to me, and they would come to the office directly to me and bypass it. And then it got to the point NASA just backed off and let me do what I wanted and let me do my thing. So I'll tell a fuller story of this. There's another organization that's interested in me telling the non-Norman Rockwell version of my NASA career. And if they videotape that, I'll send a copy of that to this organization. But I want you to understand that time at Sinclair came at the right time in my life to make it possible for me to be the full astrodynamicist that I could be the best that I could become.
That's so crazy, and just how random things can be like that, right?
Yeah, random. Yeah, you can talk, you can be prepared, but
right.
I put a lot down being at the right place at the right time. I'm in the computer lab working on the 1620 FORTRAN. If I didn't take that job, and so much is random. I don't put it down to any particular skill I had. I had it, I taught it, but so much is random in life. Being at the right place at the right time.
Asa, thank you for joining us.
Mm-hmm.
That was absolutely fascinating, even though most of it sailed right over my head. That's okay. It's super cool to see one of our favorite little computers used in such productive way, because a lot of what folks used home computers for was gaming and not other sort of lesser activities, and that you put it to this really important use, and it was sort of pivotal in your work. That's amazing to me. Absolutely amazing. Thank you.
Thank you. And please, if there's anybody on do my basic gotcha,
I'll reach out to you. Yeah, we'll get that solved.
And that of anyone who would program this base, I really appreciate it to become part of the archive.
Yeah, we'll hook you up.
Okay.
All right. Thank you, sir.
Thank you.
Our next meeting is Labor Day. September 1st is the first Monday of the month. So our next meeting will be 9 p.m. Labor Day, September 1st. Thank you all for hanging out and persevering with us. Again, thank you, Asa. Absolutely fascinating. Loved hearing all this stuff.
I'm sorry I took all of your time.
Please. It's fascinating and so interesting, and part of what my goal, not just in hosting these meetings, but also is to archive stories like this. So this the perfect Venn diagram of getting your story and archiving your story.
Thank you.
All right, thank you, everybody. See you in several weeks.